Hello and welcome to our next video on this Cavendish experiments. Today we're looking at is the Cavendish experiment a fake? We're going to focus on that today, and we're up to number 7. So basically where I got to was, as I just started creating this experiment, I had to, if I have to challenge this experiment, calling it a fake, I have to make something better. So I believe that's what I've done. I've made something, I think I made possibly the most accurate Cavendish experiment yet made. So I think I might have the sort of, maybe to challenge someone, you've got to, in my point of view, certainly as a Christian, I certainly have to make a statement with an experiment that has to be more accurate, rather than call this guy a fake. So some of the boxes that I ticked were to alarm me that this is a fake was maybe he wasn't a fake, and maybe he was measuring something else, but someone else has distorted the truth. So there's another thing in Cavendish's favour. So the first box that I ticked was this big G 666 times 10 to the minus 11 thing. Whoa. Okay, was he really measuring density? This is 1798. We really haven't proved the Earth is spinning. The big one now is the Earth. Is it actually Earth's round for a start, or a sphere, or is it flat? A lot of people still believe it's flat, and the number one would be, is it actually spinning? They haven't really determined that yet. So 1851, we need Foucault with his experiment to do that. So measuring the density, drop everything, measure density. So the next box to tick was, it's actually Michell's experiment. So now Michell was a Christian minister. He goes to his congregation every Sunday with this Holy Bible, and in page 1 of this Holy Bible is a lie stating that the Earth is flat. So what's he do? Does he go to his congregation and say, look, just ignore that first lie on page 1 and we'll just move on, the rest of the book's true? So I think Michell was the inventor of this concept, this invention, this experiment. He was the originator of the experiment. I believe he was really looking for something else, and I believe it was the looking for the Earth was spinning or not. This is just a big detour. This is someone else has got into history here and started remanufacturing history on us. Number 1 was this: the timeline of the experiment's been broken. So we've got Michell in 1783 he has the concept of the experiment. 1793, Michell dies, and so-called sometime after 1793, between 1798 and 93, a gentleman by the name of Francis Wollaston, he picks up the experiment and hands it on to Henry Cavendish, who completes the experiment with this extremely complex apparatus we don't know what Michell's apparatus looked like, so we just assume that Henry Cavendish copied it and we have to take his word. But we're still 1851 before Foucault comes on the scene and proves the Earth is spinning. So I believe he was more or less trying to find out whether the Earth was spinning rather than looking for density. Anyway, the next alarm that rang was, why did Cavendish use a horizontal pendulum? Horizontal pendulum is the most complex apparatus you can use to determine this attraction of two masses. Now, you've seen my experiment with the vertical pendulum. Done simple, anyone can do that. But I know Cavendish has to have this big complex experiment with an apparatus that needs a special room. It needs to be airtight. Now, you and I are not going to get we're not going to be able to evaluate that experiment. So it's got all the hallmarks of, like, yeah, this works, trust us, but you can't reproduce it because it's too complex and too expensive. So big tick there. Why did he use spheres? Use spheres. And he dangled them. So he thought you had vertical pendulums on a horizontal bar. Now, maybe it was to increase the sensitivity. I don't know, but something weird going on there. He had trouble dampening the oscillations. Now, unless you dampen those oscillations, you may as well, you're measuring the noise. Now, the previous experiments I did will show you that. So, and also he's looking at this oscillation going left and right across the centre point, and it hasn't clicked in his head that if this thing is oscillating left and right and not moving, then that's a big indicator that the Earth is stationary. Now, you've just seen 3 experiments I've done that shows that you'll get a 2-to-1 ratio. So go through those experiments if you want to catch up on that. This swinging mechanism, now, he tried to dampen the oscillations with his torsion bar by swinging weights left and right of it to try and dampen the oscillations. Now, I can dampen the oscillations by walking across the room and jiggling the beams on the room, and I can make it stop. But that's not the mass of my body doing it, that's just some mass moving. It's like those experiments you might see where you can actually buy this apparatus, this Cavendish experiment that you can use in universities and demonstrate it. Same thing, they're oscillating 2 lead weights or 2 masses either side of the apparatus. Now, to do that, you would have to have an extremely strong mechanism, and possibly on a granite base, to not influence the torsion of the system. You'd have to isolate, decouple your swinging motion from the mechanism measuring. A huge amount of cost, and you're looking at granite beams and machinery to decouple. But he decided to swing left and right. Now, weird. We'll look into that later as we go. Again, why do you use spheres? This one here deserves 3 ticks. I go this one 3 ticks. 1, 2, 3. Because why didn't you just use a compass? If he was going to use the horizontal bar, why didn't you just use a compass? It's all set up, bouncing on a needle. Why don't you bring a mass left and right at that? So why go through all this mechanism, this huge apparatus to demonstrate this when you could have just used a compass? All right, so let's get on to my experiment now, and I'll show you, we'll go through the experiment and I'll give you details of how it works. So let's go to that now. All right, well, here we are with my setup. The centerpiece here is our plane pendulum number 4, which you're all familiar with, our horizontal laser. The vertical laser has been disconnected and replaced with an optical encoder disc. Over here we have a up-down counter, which can actually demodulate this quadrature signal to give us a clockwise and anti-clockwise direction. A 1 metre horizontal carbon fibre hollow beam, and suspended on either side is a red and a blue glass sphere. They are 50 millimetres in diameter, and over here on the ground, left and right, we have our selection of masses that we can bring closer to simulate looking for our deflection. The suspension cable has been replaced with the optical fibre. I've been using optical fibre for our suspension cable. It's been replaced with a 1.5mm carbon fibre cord cable, which is a linear. There is no the fibres are linear in it, so there's no twisting bias. At the moment, I'll take you up to the roof, show you these, and also a digital encoder on the roof, which I use to line up the system and measure the torque variation. I'll just show you that now. What I'll do is I'll move the carbon fibre rod. Just watch our number here, which is 1151. I'll zoom in on that a bit for you. Now I'll move this I'll move this carbon fibre rod, and you should not see any movement in that. It's swinging quite a distance there. Coming back and giving you a zoom. Still on 1151. So you can see that quite a deviation, and 1151 hasn't changed. That is our resolution of our I guess it's the glass fibre rod's torsion. So I'll take you up to the roof now and just show you the optical encoder up there. So here we are at the ceiling, and you can see the encoder mechanism. We're coming down, we'll see a brass knob, which is my detent, which can stop the cable twisting at any time, and underneath that is a 100 tooth cog, which I can actually detent to any position. That is a fiberglass cable of 1.5mm. I've just realised I should have said that. It's fiberglass. And a better shot from looking underneath. So at the moment the counter, the up-down counter, is logging the digital encoder on the roof, which I use to line up my laser and look at that node bias, which is the equilibrium point of the system, and I can line up my laser. So what I'm going to do up the roof here now is move that optical encoder half a tooth. Now you might see something, you watch that counter down below. Bit crazy probably. 1170. Okay, that's probably half a tooth movement on the top. It's a 2000 count optical disc on the top, and I've got a 2000 count optical disc down below here, which I haven't quite engaged because at this stage the system is wobbling too much. So when the system settles down, I will actually engage that optical reader, which is a Heads 9040, which is pretty high resolution optical reader. Now, one more little trick I've got. I'll just show you that now. Let's reposition myself. Alright, I've just engaged the optical encoder reader on the disc below, and I've disconnected the counter from the optical encoder on the roof. It's no longer needed, but here's my little trick. Remember, we're around about that 1130 mark. It's been bumped a few times. So here's my little trick. Remember I said that was a hollow carbon fibre cable? Well, I have a little trick. I can insert a string of magnets into this section. Oops. Alright, here we are. I had a little oops moment there. So what I can do is insert a series of these minute magnets into the system. And create a giant compass. That being a hollow carbon fibre tube. Now, when I balance that, you'll see this thing swing around and we'll get a new reading. So stand by for that. Alright, it's been 30 minutes. I can't wait any longer. I was going to try and gauge the bottom optical reader, but this thing is still not settled and I don't want to scratch the optical disc. So this was just a demonstration, but you should be able to see clearly that those two glass spheres have actually swung around and they're now, the whole system is pointing north. I'll remove the magnets now and we'll go back to a normal Cavendish experiment because this thing takes forever to settle down and it's getting late now. These experiments need to be done at night. It's winter time here in Canberra and I need to run the heaters, and the heaters blow air, so when I go to bed I switch off the heaters, and this house otherwise this house is just crazy trying to live up here with this thing. I need the top floor for the angle of the laser to give me the range, and I also wanted a second floor to give me, I didn't want a lot of mass underneath this object, which is concrete, so it's just a wooden floor up the top here. Alright, so next setup should be actually seeing the experiment in place, so stand by. Okay, here we are at 1655. The temperature is 18 and the humidity is 76. Our count is oscillating between 1330 1300. Okay, that's not too bad, it's settling down pretty quick. The heater's still on, so we're getting a lot of movement in the air. And we're getting, it's erratic at this moment. 1350s. I'm walking around. I'll take you up the other end and let's see if we can see the laser. Stand by. Alright. I haven't bothered to measure the laser at this end because it's still moving quite a bit. We're 8.5 metres away. And it looks like it's swinging. Oh, hard to say. The gap in that door there will be about 250 millimetres. Looks like it's going back now. Look, okay, it's gone off something here. The piece of furniture blocked it now, so alright, 17, nearly 19, oh hang on, that's 1900, sorry, my mistake, that was it's coming up to 1900, that was 1800 before, sorry, 6 o'clock. Anyway, it's been 5 minutes and I'm sort of quite happy with that. As you can see, this digital readout is so much easier than that laser at the other end. I can actually stand up this end and do experiments without turning around and watching some remote wall 8.5 metres away. No, yeah, it's still getting into the climbing it. The heat hasn't kicked in, so that would be me just walking around the room, creating air currents. Alright, what we'll do is we'll come back just before I go to bed, and this thing should have stopped hopefully, and we'll see what happens then. So stand by for that. I'll quickly give you an idea of the resolution of this counter. Unfortunately, it's only 2000 counts per revolution. Time is 1940, and 1340 is our counter. See the bulb moving across. Right, looks like it's coming up to halfway point now. Halfway point now, 1365. Going clockwise, so the count's going up. Okay, we've just moved 25 millimetres, the other halfway, 1378. I sort of moved around a bit to create some more air to give you an idea of, get this thing swinging further. Okay, we're coming back to counting down now. So we're going anti-clockwise. Halfway point, 1365 again. And once again moving the 50 millimetres on that line, 1345, something like that. Alright, that was just a demonstration of the resolution, but our laser at the other end, 8.5 metres away, will give us a much better indication. See you in a couple of hours hopefully. Alright, here it is at 04:45 in the morning the next day. So our counter is stopped at 1355. And we still have movement in our suspended bobs. It's slowly moving counterclockwise. The temperature is 15 degrees. I was hoping for a frost. Okay, so this means the experiment can't go ahead. What I'll do is I'll show you the laser at the other end. So the laser at the other end is moving quite a distance as well. which is obviously typical of these experiments. Alright, I think I was hoping for a frost, but we didn't get one. It's actually raining, so we'll get quite a lot of deviation. Alright, I'll see you in the morning when the sun's up. Oh, here we are at 9:10 the next day. The sun is out. I've reset the counter, and our plumb bob, or I guess, or pendulum is moving very slowly at the moment. It's counting down very slowly. Which means it's going in the anti-clockwise direction. Obviously going clockwise now, it's counting up. The temperature is 17 degrees, humidity is 77, something like that, but the roof is getting hot. This is a truss roof, so it'll be expanding and there will be movement, but for this experiment to actually work, it must come to a standstill, clearly. The laser at the other end is moving quite a distance, as you would imagine, but I can only surmise from this point that Cavendish, he either falsified his experiment deliberately to create this illusion of searching for big G, and the density of the Earth experiment was a decoy or distraction, because I believe that would have been Michell would have been looking for the Earth spinning more than anything else. He wouldn't have been interested in the density of the Earth. He was more interested in if the Earth is stationary. Now here we have a mass, two masses suspended on a horizontal pendulum bar, oscillating equidistance. This can never happen on a rotating Earth. The Earth must be stationary. And I believe this is what Michell was trying to prove. And Cavendish's experiment was just a big detour, distraction. So you can clearly see this thing oscillating across the centre line, across those two numbers, counting up and down, equidistance. How can this happen on a rotating Earth? These masses have inertia. This should not happen. Alright, anyway, that's my summation at this stage. Obviously there's more experiments to do. We can use the magnets and create a more stable situation with the compass setup. But to me, I've got no doubt that the Earth is stationary from this experiment, and this is, I believe, what Michell's trying to find. Alright, I think that's enough. Thanks for watching, and we'll see you in number 8.